Hello students, now we will see the next concept, asymptotic notation. It is very important concept in algorithms. In the last video, we have seen that the total step count is useful to represent the time complexity of an algorithm. So we have seen up till now, this step count is a nice function of input, that is number of elements, or maybe its function of output or some simple characteristic. But this particular thing is not always true for the all algorithm. For example, we can take the example as a binary search. In the binary search, we have the sorted array and we have to search a particular element. Suppose the elements are like 1 and then what the 5, then what the 10, then 15, then suppose 20 and suppose 25. So they are stored at the array indices like this. 30 at index 6. Suppose that I want to find out the 15th one. So what we are going in the binary search is, the low is nothing but what the starting indices, end is nothing but what the ending indices. So low plus 1, low plus end divided by the 2, that is mid. So the mid is over here. So it is going to find out that is 0 plus 6 divided by the 2, that is what the 3. So we will go to the location 3 and we will see that whether the element is there at the location 3. So I want to search the 15. So in the one comparison, that is in the one step count, I am going to search the element 15. Suppose that I want to find out the element 5. So 0 plus 3 divided by the 2, it is nothing but what the 1. So I will go to the location 1 and I will search what the 5. So with the two number of comparison, I will get the 5. Suppose I want to find out what the 25. Here my low is what, first I will compare with the 15. 25 is greater than 15. So I will discard this particular array and I will only take the other second half array. So my low is 4 and my what the end is 6. So the 4 plus 6 divided by the 2 is 5. So I will what the search the 25 in the two number of the steps. So we can see that the n is going to be same, that n is 7. So input is 7 elements. For same input, depending on what the element we want to search, the number of the program steps are going to be vary. Same for the linear search. Suppose this is my array, I want to search the element linearly, that is sequentially one by one. So for 1, I require only the one comparison, that is one program step, and for the 3, I require 30, I require the 7 program count. So we can see that for many algorithms, so for the same n, the step count is going to be what the vary. So we are going to determine, or we are going to have the 3 step counts for the given parameter n. That is what the best step count, which is going to represent the minimum number of the step count. Average step count is nothing but what the average number of the step count for a given parameter, and the worst is what the maximum number of the step count is required for that given parameter. We always use this step count to compare the time complexities of the algorithm. Suppose that this is my step count for one algorithm, this is the second what the step count for my second algorithm. So we can see that you can take any value of C1, C2, C3. So you will always see that after a particular point, my C3n is going to be faster than my first algorithm. So we will take the example, suppose C1 is equal to what the 1, my C2 is what the 2, and suppose my C3 is what the 100, and you can see that when n is what the greater than 98, so you can see that after that my C3n is always greater than my C1n square plus C2n. So what I want to say that this n, which is called as what the even breakpoint, so my C3n is always going to be faster than the first one, and that n will be what the break even point is going to be there. Next is what the asymptotic notation. So we will use some mathematical function to describe this complexity instead of the exact step count. So this asymptotic notation will treat the algorithm as a function, and they will classify these functions into the three classes. So the first notation is what the theta notation, which is going to represent the average step counts, function of the average step count. The big O is what it going to represent the function of what the maximum step counts, and the omega is going to be represent the function of the minimum step count. So here these functions are there which are going to describe or the running time complexity. We are going to use these notations to show or describe the running time of the algorithm. So we will see the first asymptotic notation, that is what the big O. So we can say that f of n is the big O of g of n when this particular condition is going to be what the true. So there exists always one c and n0 in such a way that my c multiplied by g of n is always greater than my f of n. So my time complexity of the algorithm, which you are representing in the f of n, is never greater than this c multiplied by g of n. So I can say that this g of n is asymptotic upper bound for f of n. So we can take the example over here. So suppose my f of n is 3n plus 2. Okay. So we have to find it out. So we have to find it out the g of n in such a way that, okay, so c multiplied by this g of n is always greater than what this f of n. So suppose I will take the example, the c is 4, you can take any value of c. So that time if suppose my n is what the greater than or equal to 2, for this particular value I can say c multiplied by g of n is always greater than my f of n. So I can say that my big O of g of n, that is big O of n, is what the upper bound for my f of n. So we can see that this g of n describes specially worst case scenario. Above that, the time complexity is not going to be there. So we can solve the same thing. So here my f of n is 10n square plus 4n plus 2. So we have to find out the c and the g of n in such a way that c multiplied by g of n, okay, is always greater than this if there exists one n which is what the greater than or equal to what the n0. So in this way we have to solve this example and find out the big O of n. So the next asymptotic notation is omega. So in the omega we will say f of n is omega of g of n if there exists positive constant c and n0 in such a way that my c multiplied by g of n is always less than f of n. So we can see that this is f of n. So my time complexity of the algorithm is never going to be below of this g of n. So this is going to be represent the lower bound for my f of n. So what we will do, we will take the same example. You can take the same example and see that, okay, you have to find it out the c and the n0 in such a way that the c multiplied by g of n is always greater than what the always less than f of n. For example, we will take the same example, 3n plus 2. Okay, so what I will do is I will take the c is 3, okay, and the g of n is what the n. So we can see that my 3n plus 2 is always greater than or equal to, for the n is what the greater than or equal to 1. So in this way there exists always one positive constant c and the n0 in such a way that for this my f of n is always greater than and equal to what the c multiplied by g of n. So here my omega of what g of n is n. So it is going to represent lower bound for my f of n. So in this way this is the second asymptotic notation. So same way we can solve for what the next examples. The third and the last asymptotic notation is theta. So the theta is going to be represent the tight bound or the average case scenario for the algorithm. So you can see that my f of n time complexity is never beyond this C2 g of n and never below than C1 g of n. So it's like a sandwich. So therefore g of n is always asymptotic tight bound for my f of n. So what we will do? So we will always see that we have f of n and we have to find out the g of n and the c1 and the c2 in such a way that this particular equation is going to be satisfied for the all values of n which is greater than equal to n0. So we will see one example so you can understand. Suppose that my time complexity is what the 10 n cube plus 5 n square plus 17. So here what I will do is I will find out the C1, I will find out the C2, okay, and what I will do is I have this f of n, okay, this f of n. So what I will do over here is, so C1 of g of n, so g of n is n cube, and here my C2 of g of n, so I can see that my f1 is always greater than my C1 g of n and always less than my C2 of g of n. So in this way my time complexity I will represent as what the theta of what the n cube. So in this way it is nothing but what the it is going to represent this particular thing is going to be represent both upper and the lower bound for an algorithm running time. So in this way you can solve the another example over here. So the summary of the notation. So we have used the three notation describe the time complexity as a function by using this three notation. So because of g of n, here my f of n is always less than what the g of n. Omega, in the omega, my f of n is always greater than that g of n. So here it is going to represent the upper bound, it is going to be represent what the lower bound, and the theta is going to be represent the lower and the upper bound, okay, both expressed. So you always remember that big O is the upper bound. Suppose if I have an algorithm whose time complexity is big O of n square, so maximum time is big O of n square. Maybe algorithm runs into the big O of n for some input. So conventionally, whenever I will use the omega is the lower bound. So whenever my algorithm is n log n is my omega, so that time my algorithm can be run into the n square or 2n. So this is lower bound. So this is what the minimum time which is required for that algorithm. It may take more than that particular time. So the next is common rate of the growth. So for the constant running time, we will represent the complexity in terms of what the theta of 1. So whenever we will represent the time complexity, normally we are using the theta. If you want to represent the best case or the worst case, so that time you will use the worst case by using the big O and the best case by using the omega notation. So whenever my time complexity is a linear growth, that time I will use what the theta of n. Whenever it is a logarithmic, I will use theta of log n. Whenever I will use the n log n, I will use the theta of n log n. Quadratic, theta of n square. Polynomial, theta of n square, n cube, whatever. And exponential is 2 raised to n, 3 raised to n. So in this way we will represent the time complexities. So these are the some analysis. So the time versus the number of the element. So whenever my time complexity is what the constant, so that time the it is the big O of 1. So log n and linearly, then it is linearly, then n square, n cube, and what the 2 raised to n raised to n, whatever. So in this way, for small input, I will require the more time to complete that algorithm. So if it is a constant, so it is not depend on the number of the input, so the running time is going to be constant. So whenever we will have the two algorithms with a different time complexity, so we can compare it So if suppose I have one algorithm with big O of log n and another algorithm with big O of on, so what we can do is we can always see that the algorithm which has the time complexity log n is better than the big O of n. So in this way, this is the time required depending on the number of the instance n. So this is a summary for this particular point. So we have analyzed the function asymptotically. So we have seen that only the leading term is important. So what is meant by the leading term? So if it is what the 3n square plus what the phi n. So we have seen that phi n plus what suppose 10. But here only the leading term is important. The constant don't make a significant difference, and the following inequality hold asymptotically. So C is always less than log n is always less than n is always less than n log n. Okay. So in this way, the algorithm if this n log n is always better than what the algorithm with the theta of n square complexity, n cube complexity. So now we will see that suppose we know the step count, how we will represent that algorithm in terms of the big O. So this is very simple algorithm finding out the area of the triangle. So require the 3 step count. This is 1 step count, this is 2nd step count, this is a 3rd step count. So we have the 3 step count. So my f of n is 3. So now we have to find c multiplied by g of n, which is always greater than the t of n, because we have to represent it in the terms of big O. So I will say that 3 multiplied by 1. So my c is what the 3 and my 1 is nothing but what my g of n. So c multiplied by g of n is always what the what you say greater for what the n is what you can say n is greater than 4. Okay, so in this way you have to find out the c and the n0, and you have to find out the g of n, and you can represent the time complexity of an algorithm in terms of the big O. So here we can say that time complexity of above algorithm is what in order of 1. So the second example, we have to find out the sum of the array element. So we have the this particular algorithm. So here one step, and here what may be the here what we will see is number of steps and here it is also what the one step. We will count out it's near about the 2n plus 3. So that time what we will do is over here is we will find out the c and g of n. So we will find out the c is what the 3 and the g of n is n, which is always greater than this 2n plus 3. So what we can see that my tn I can represent in the big O of g of n, that is big O of n, for the what the n is what the greater than equal to what the 4. So in this way I can represent the time complexity of an algorithm in the order of n. So in this way, if you know the step count as a function of n, so we will say it is a time complexity, that is t of n, and after that we will write that equation and we will find out the c and n0, and we will see that c multiplied by g of n is always greater than what the f of n, that is t of n. We can find out, or we can represent the time complexity in terms of the big O notation. So in this way you can have the exercise. So here my c is this, my g of n is 1, so I can represent this time complexity is big O of 1. Here I can find it out the c and n0 in such a way that my time complexity is going to be greater than equal to this particular function f of n. So here also my time complexity is what the big O of n for some kind of values of the c and what the n0. Okay. So for any query related to the asymptotic notations, please write down at psfeeder@picd.edu. Thank you, students.